Today in class we thought about walking rates and how you can see them in graphs, tables, and equations. For tonight's homework, make sure you've completed page 6 so you can correct it with this section. In the first problem, we're told that 4 friends who are part of the walkathon make the following representations of their data. Could any of these relationships be linear relationships? Well, based on what you saw today, linear relationships need to have a constant rate, just like proportional relationships. However, unlike proportional relationships, they don't necessarily need to go through 0, 0. And we know that they have a constant rate because they create a straight line with their points. So there's lots of different ways to approach these problems. Let's look at a couple ways. For George's walking rate, I'm noticing here that it's going up by 1 each time. And I notice that the distance is going up by 2, then by 7, then by 2. So it's not looking like a constant rate. So I would say that George's walking rate does not look linear. Elizabeth's walking rate, I can see that it goes by 2s for time, and I see that the distance is going by 3s. And I can continue that pattern so it continues the whole way through. So I would say this does look like it's linear. And if I wanted to find the exact walking rate, I could take the distance and divide by the time. So 3 over 2 seconds, which means that we're going about 1.5 meters per second, per 1 second. That shows me that there's a constant walking rate. Now I've got Billy's walking rate from this equation. And I'm noticing that it fits this equation that we were talking about in class. Distance equals the rate times time. And so in this case, I have a constant rate of 2.25 meters per second. And so this tells me that this is going to be a linear relationship. It's going to look like a straight line when I graph it. Then I've got Bob's walking rate. So it says time equals 100 divided by the rate. T equals time, R represents walking rate. Well, that looks a little bit different than anything else I've seen. One way to check this too would be to graph it. So for example, I'm basing the rate and the time here. I'm connecting those two. So for example, if the rate is 1, right, 100 divided by 1 would be 100. So I'm just going to make this 1, I'm going to make this 100. If the rate was 2, 100 divided by 2 would give me 50. So about halfway through here. Then if the rate was 3, 100 divided by 3 would give me 33. So I'm noticing that this doesn't quite look like a linear pattern. Again, I can keep checking. 100 divided by 4 would be 25. So that would be halfway between. So I'm noticing a little bit of this shape here, and that is not a linear relationship. It's not going down by the same amount each time. One of the things you also might have thought about is how with a proportional relationship, there should be a constant multiplier. And in this case, it's not that I'm dividing or multiplying by 100 each time. I'm dividing by a variable each time. So if I'm not dividing by a constant or multiplying by a constant, then this is not going to be a constant rate of change. So you should have that Bob's walking rate is not linear. Now we're going to find the unit rate and use it to write an equation relating the two quantities. So $150 for 50 t-shirts. Well, I might think about my unit rate here. Is it more likely that I'm going to say how many dollars per shirt or how many shirts per dollar? Well, usually we would say dollars per shirt. So if it's $150 for 50 shirts, what would the cost of one shirt be? I can see my scale factor. I'm going to divide by 50 or multiply by 1/50th. And 150 divided by 50 would give me $3. So in other words, it's $3 per shirt. So for an equation, I could say the cost equals 3 times the number of shirts. And you can choose the variables that you're going to use here. Now it's $62 to rent 14 video games. Same kind of unit rate, $62 for 14 games. So how much for just one game? So if I divide by 14, I get approximately $4.43. So I'm going to say it's $4.43 per game, and my equation is going to be the cost of the games is 443 times G. Then I have 18 tablespoons of sugar and 3 glasses of Bolda Cola. So I want to know perhaps how many tablespoons of sugar per glass. So 18 tablespoons in 3 glasses, how much in 1 glass? I'm going to divide by 3, and this would give me 6 tablespoons per glass. So for my equation, I'm going to say, glass. I'm going to say that the tablespoons equals 6 times the number of glasses. Now for 3, we see that the longest human-powered sporting event is the Tour de France cycling race. In a particular year, the average speed for the winner of this race was 23.66 miles per hour. I'm hoping you see that and you're thinking, that sounds like a rate. In that same year, the race was 2,292 miles long. That sounds like a distance. So how long did it take the winner to complete the race? That sounds like time. So we've been talking about a formula, distance equals the rate times the time. So the distance, 2,292, equals the rate, 23.66 times the time. So how can I solve for t? Well, based on what you know about fact families, I know that these two numbers multiplied together are going to make the other number. So if I divide 2,292 by my rate, 23 and 66/100ths, I should get my time. So when I divide those values, I get approximately 96.9, and that means it's going to take that many hours for them to complete the race at that rate. That's it for tonight's homework. I hope you'll be ready to move on to more linear relationships tomorrow.